Record. Okay. So 2.3 is the structure of ionic solids. Okay. So what do we mean by ionic solids? Oh, it should be over here. What do we mean by ionic solids? Oliver?
Ionic compounds in a solid state.
Yes, ionic compounds in a solid state. So when we talk about ionic bonds, right? Oh wait, before we get too far into this, I reminded you that I reopened the exam. Also, only one person has paid for their AP exam. You need to go talk with Miss Brown, because I think I only had one person. She sent me an email. Go talk with her. You need to go pay your stuff so that you can take the AP exam. You have the rest of this week to get that done.
Who one person?
I think it was you, but I would just check with her. Okay, just go talk to Mrs. Brown. Okay. So ionic solids. So the classic example of an ionic solid, salt, right? Sodium chloride, okay? So sodium chloride, when we look at ionic compounds, and we're going to be talking about this a bit, and we've talked about the size of atoms, right? Remember that atomic structure or atomic radius is important for atomic structure. So between sodium and chlorine, which has the larger atom? Sodium. Why?
Because they're in the same room, meaning they have the same levels of.
So they have the same number of shells.
Except for one of them has higher charges.
But chlorine has more protons and more electrons, so they pull on each other more, right? So sodium is like this. And chlorine is like, this shows up well. Blue doesn't really show up that well. Green shows up okay. Okay, so you have sodium chloride. This is, remember when we talked about intramolecular forces last time, intramolecular forces being the forces between the atoms in the molecule. Now we're going to look at a little bit about intramolecular, so between molecules, okay? So if we look at this, the rules for these compounds and how they're going to arrange themselves is they maximize attraction. So the way they align themselves is in such a way that maximizes the attraction between particles and minimizes the repelling forces. Okay? So if you are maximizing the forces that are attracting each other, you'll end up with, maybe I shouldn't have done, I don't know, whatever. You'll end up with and what will happen is it will make it arrange itself in such a way in kind of in a lattice structure like this, okay? Does that make sense? Why this is doing this? Does that make sense why that is? Because each molecule or yeah, each molecule wants the positive end touching the negative end of the other molecules. The sodiums don't want to be by each other, and the chlorines don't want to be by each other. Because remember, I mean, they're just like magnets, right? Because they're positively charged and negatively charged, right? So we have over on this side, we have, this is the positive side of the molecule. This is the negative side, right? So positives and negatives want to be by each other. Negative, positive, negative. You already took notes on this in the text? Are you sure? I don't think we've done reading on this.
Earlier in the course, I have notes on it.
Really?
The whole line structure and how the negative right here, negative goes to the positive.
Oh, and ionic bonds, yeah. But we want to just specifically, yeah, we're just focusing on it. So we get that, okay? So sometimes you'll be asked to make a representation of an ionic solid. And it's kind of tempting to just do, so let's do like lithium fluoride, okay? It's tempting to do lithium fluoride where you just do like a, so the black is lithium. Right, and then red is fluorine. So why doesn't that work? Yeah, or
Because then the ones on top are near each other.
right.
So you got to form like a checkerboard.
Yeah, it forms a checkerboard, okay? Because every other one will be flipped around the other direction as to maximize, and this is the terminology, maximize attractive forces and minimize repulsive forces. Okay? So that is the entire topic of 2.3. All right? And I feel like that they didn't need to make that its own topic, but that's what it was. Yeah.
I mean, maybe they want you to do like optimization for where the two forces interact, you know, like if the repulsive forces are that much stronger, then you just overcome the attractive ones, and so you have to like
Yeah.
balance where they're.
Right, and we'll get into more like complex molecular geometries later when we start talking about like trigonal, pyramidal, and stuff like that, or tetrahedral and all that stuff. But like when I was researching exactly what they wanted me to teach on this, like that's it essentially. Like make sure the students understand that repulsive forces are minimized and attractive forces are maximized. It's really all that they want from that topic. Okay. Questions on ionic solids, structure of ionic solids?
Are they all lattice structure?
So there are ionic compounds that can have multiple atoms, right? So they don't always make that shape.
But are they all like papers from each other?
Yeah, I mean, the principles remain consistent.
Okay. So
There's always a repulsive force between commonly charged particles.
okay. So like an atom has to be next to or surrounded by different types of atoms.
Yeah, so it wants to be surrounded by other atoms that have a different charge.
And therefore two atoms has to be that structure.
Yes. So this is exactly what they have written in their language here. Represent an ionic solid with a particle model that is consistent with Coulomb's law and the properties of the constituent ions. The essential knowledge is the cations and anions in an ionic crystal are arranged in a systematic periodic 3D array that maximizes the attractive forces amongst cations and ions while minimizing the repulsive forces. That is a very long sentence.
Summary.
Yeah, I mean, the summary is just anions are close to cations. Not cations, cat ions. And repel similarly charged particles. Similarly. Repel? Yeah, isn't it? And repel similarly charged particles. Really, that's
It's you got the basic concept.
yeah. And like the fact that and this seems a little bit obvious. Like they say the cations and anions are in an ionic crystal are arranged in a systematic periodic 3D array. So what it means is it's a repeating pattern, right? That can be predicted. And of course it is 3D, and we only did 2D models, right? We only did 2D. So remember that this is not what happens, right? It's like this, right? We only did 2D representations, but if you look at an ionic solid, and you can see something like this, right? There's salt once again, okay? So not only do they make the lattice structure in two dimensions, but also in 3 dimensions, right? So you go sodium, chlorine, sodium, sodium, chlorine, sodium. And it repeats in all directions, the pattern, okay? That's really all that they want us to understand from this topic. A 3D checkerboard, yeah. By the way, I am pretty sure, all right, I've got to know. I've been curious about this for a while. I'm pretty sure the checkerboard, etymology. Pretty sure. So it comes from a game of chess or checkers. An ornament, so a checker, an ornament with a checked or checkered design. Checker, table covered in a checked cloth. I'm pretty sure, okay, so for instance, I know that you're all like, this has nothing to do with chemistry. And you're right, it doesn't. But there are things that are important to understand. So Czechia, is a country, okay? Czechia. Well, so they say the Czech Republic, but the term that is most commonly used these days is Czechia. And it has, where is it? Czech. They use a red and white checkerboard. You see this? They use the red and white checks. And I am pretty sure that the word checkers comes from the Czech, like the people, the Czechs, because that was on their coat of arms. I'm pretty sure. And I can't find any evidence to support that, but it just seems like too much of a coincidence that a checkerboard is a, anyway.
Well, if you're ignoring the confounding variable, maybe the Czech was looking for inspiration and they thought, well, how about we use checkerboard?
Right, because it's the same.
Yeah,
it's the same word.
The same.
Yeah, maybe. International. So, like, even there, look at this. Where is it? Like, look at this. Look at it. Look at it. It's just checkers. Okay? It's just, anyway.
You think there are countries that are on average than most countries in checkers?
all of the best checker players come from the Czech Republic. Yeah, maybe. Okay.
Because they're playing it on the flag.
Okay. All right. Now that took up way more time than it should have done. Let's talk about 2.4. So we did 2.3, 2.4. So topic 2.4 is the structure of metals and alloys. Okay. Structure of metals. Not allows.
I'm sure like a austenite, pearlite, and ferrite, the cementite structure.
I mean, we could look them up, but really,
I can draw them from memory, so you don't need to look them up.
of course you can. Okay, so
You can draw the heat map to the carbon distribution.
So when we talk about the structure of metals, when we talk about the structure of metals, most of the time what we're looking at is it's representation of positive metal ions. So we'll do. So
what's the difference between metalloids and non-metal alloys?
We'll talk about alloys in a minute.
Alloys,
Wait, this is about alloy.
So this is a representation of metals, okay?
metalloids are that little bag on the table, but alloys are a mix of the two, like the transition metals. Probably not even just transition metals.
So
I don't think bonds. I think it's just like you mix them together.
all right, so when we look at our metallurgist over there. So when we talk about metals, oftentimes metals are just positive metallic ions surrounded by free electrons. Okay? So the electrons just kind of are there, okay?
So what is it, like liquid metal?
No, it's not liquid.
But you can note it the other way, so you have positive charges. Semiconductors.
Yes, you can make semiconductors out of it. We're just talking about metal structure, okay? So if we look at this, let's look at this image really quick. So you can see that, so we have the metal ions, the positive cations, and the electrons are really kind of just free to move. 11th grade. No, year 11 is 11th grade in like Europe. So you have the electrons that can just flow around. They're free electrons. Okay? Free electrons from the outer shells of metal atoms. So they can just, the valence shells of the metals are just kind of, it's free love, right? It's like just be what you want to be. Go where you want to go. I'll share some of my electrons with you if you share some of yours, and it's just like, it's what? It's free real estate. Yeah. It is, okay, it's pretty straightforward, all right? So it is, did I get rid of this? Oh, no, I didn't. Okay.
This is metallurgy day.
We're not covering metallurgy, okay?
We can't even have one day?
No.
What if we covered all of metallurgy and semiconductors?
We're not going to do P doping and like all sorts of, yeah.
What do you mean we're not going to do P doping?
Oh, well, we might when we get to like electrochemistry and stuff. Dibs. Okay. So this is topic 2.4. Yep, structure of metals and alloys. So when we talk about the structure of metals and alloys, so it's metallic cations are in a structure with free electrons. Electrons from the valence shells with free electrons from valence shells floating around. That is not how you spell floating. Floating? There we go. And again, it's not really like floating, right? Electrons aren't so much, they're just kind of zipping around, doing whatever they want to do. And so there's, if you were to look at it just a very specific small place of a metal, so if you were to look, for instance, at this this would be good. So if you just were to take a snapshot, which is of course impossible, if you were to take a snapshot of just these, what is this, 15 metal atoms, you would see that there was a localized negative charge here and a localized positive charge here, right? But the thing is that in metals, that those positive and negative charges just kind of flow all around.
So it's kind of like an average.
It is kind of like an average, yeah. But again, it's moving so fast. And this is why metals such as copper are so good for transferring electricity, conducting electricity.
That's the valence electrons.
The valence electrons are happy to move along. And what's interesting is that, so for instance, when you turn on a light, so when I turn off this light and I turn it back on, the time that it takes for an electron to actually get from the switch where the circuit has been completed, to get from the switch to the light, is actually kind of a long time. It takes a few seconds. But as soon as you connect the circuit, it's a flow, right? They all push each other. And so it happens at essentially the speed of light because they all move together. Yeah, it's a chain reaction of pushing each other along. Whereas it's not the time that it takes for a single electron to get from the switch to the light bulb. It is they're all pushing each other along.
So it's like an electron on it, an electron on it. It's kind of like
Yeah, exactly. It's kind of like a multi-car pileup, where one car crashes into another, and then they all just crash into the one in front of them, and that will actually move through the system much faster. Yes, Oliver.
So it's like you have a tube filled with water, and on one side, if you like connect the battery to it, then it sucks the electron from one side and creates a negative, like I guess, like a suction on one side, and that would be a positive charge in that analogy. And then on the other side, it's pushing water, and that's creating a negative charge. And so all of the electrons along the line are trying to get away from the negative charge into the positive.
Yeah, so it's and they're all moving together. Christian? Yeah. Okay, so that is the structure of metals. Now we need to talk about, there are two different types of alloys. So what is an alloy? Oliver? I know you're just dying to tell me.
It's like a slushy of different metals. You mix them all together, when they're all melted, and then you have them solidify.
Okay.
And it's
So
not that hard to separate them either.
It's
You can like
right.
bind one to another, and you can have it like float to the surface as slag.
Yes. So the metals do not mind hanging out with one another in different combinations. And they don't need to bond together. They don't need covalent or ionic bonds to be able to be in a single piece of metal. So for instance, it is very rare that you actually see a pure metal. Most metals that you encounter are alloys. So for instance, this is aluminum, but I'm sure that it has a little bit of some of different metals in it. Okay. What metals do you think are in this, Oliver? This is primarily aluminum, but it might have a little bit of, probably has some iron, and
It's a whole bunch of stuff. It's probably got everything from magnesium to a little bit of zinc.
probably, zinc. It probably has some copper.
Oh god.
You cold?
No.
I was trying to figure out why you were there.
I'm not cold, I'm just rubbing in my blanket.
The three jacket.
Okay. That'll warm you up, by the way. Just keep it right there. Okay. So bonding is not necessary. Necessary? That's not how you spell it. Is it? Huh, I guess so. To make a cohesive yeah, they're it's kind of like a metal slushy. Okay.
Is it only the metal sludge?
Well, kind of. Well, it's not like.
You can't really tell what it's
So we're going to learn about the two different types, the two basic types of alloys. Okay? The two basic types of alloys. And if we look at this. So you can find images like, yeah, this is what we want right here. Okay. Why are they using this? Why do people use?
That's the worst possible font.
Can you not use this ridiculous font?
Just use for like.
You can tell that this is for jewelry because some person is like, look at this really cute font that I chose for gold. Stop it.
Just use a dot.
Here, in World War II, they had a really cool alloy. It was like mostly aluminum, but it was the high concentration of copper. So you can look at like aluminum, copper, World War II alloy. They used it to make
Aluminium,
yeah, they used it in their planes.
copper, plain. Alloy. This is cool. Ooh. Corsair. Yeah, so anyway, alloys are really interesting because you can completely change the properties of a metal by mixing it in with other metals. Okay.
Like ferrite to cementite. Right? Right?
Yes.
Just a little bit of carbon. That's all you need.
Yes. And so steel,
Welch's properties.
no.
Ferrite.
Steel is one of the most important alloys. Steel is an alloy primarily made out of iron, right? There's many different types of steel, right? There's stainless steel, high carbon steel, low carbon stainless steel. So you can use all sorts of different types of alloys to get different characteristics. Those different characteristics can include melting point. Obviously, you can, yeah, strength and rigidity, the plasticity of the metal, whether it's bendable or not. So you can get all sorts of different density, right? How heavy something is per volume.
Very resistant
Okay.
to acids.
So there are two major types: interstitial alloys. So we're going to talk about. So let's talk about interstitial alloys. Interstitial alloys are alloys of atoms, not underscore. Alloys of metals with different or like significantly different atomic radii. Okay, so an interstitial
Be like cementite because the carbon and the iron are very different. It's hard to bend them because it warps the structure.
right. So what happens is you have these atoms. Okay, so an interstitial, we'll do 4 here. We'll do 4 here. An interstitial alloy is an alloy when you combine the two different types of metals that you fill in the space. So this alloy is only possible because you have an atom with a large atomic radius being mixed with an atom with a small atomic radius. So for instance, if you take titanium, okay, or let's do chromium, okay? If you mix chromium together with zinc, what you're going to end up with is an interstitial alloy, because the chromium has a larger atomic radius and the zinc has a smaller atomic radius.
Yeah. It actually displaces the main alloying metal because it strengthens it, because before you have like a cleavage point, like if you have a chessboard, you can just slide them.
Yeah.
But if they're warped and they're all like back and forth, you can't just slide them. It's like,
Right. So, and this alloy, so the oh, thank you. So the alloy, so an interstitial is the small atom fills in the space, fills in space between the larger atom. And that is, I mean, that is a huge simplification. It is a big simplification, but it is the basic idea between larger atoms. Again, Oliver, we don't need to get into the specifics.
you're giving an inaccurate picture of another.
We'll talk about substitutional alloys in just a second, Oliver, okay? Just relax, dude. Okay, so interstitial alloys. So the specific wording that the College Board people want you to know is interstitial alloys form between atoms of different radii, where the smaller atoms fill the interstitial space between the larger atoms. Ergo, steel, in which carbon occupies the interstices in iron. Okay. You have to use the what?
The word
Ergo, e.g. No, I think the real word that they didn't need to use was interstices.
Exactly.
Interstices occupies the interstices. Really, what you're just saying is the room in between them, the empty space between them. Okay. And Oliver, if you have an issue with this, take it up with the College Board. Okay.
They're not teaching the lesson.
I'm teaching the lesson, and I have to teach what they want me to teach. What? Do you want to be prepared for the exam or not?
I want to be prepared for the real world.
Okay, well, but this is the basis that on which you can build more specific knowledge.
Or you can build specific knowledge, which is the basis for building non-specific.
This class is like college class. This is all about specific.
Well, it is okay, but there's a difference between taking college level chemistry and college level metallurgical dynamics.
Which is way sicker.
Okay, there's a difference. So for instance, like there's a difference between, so the classes that I took most in my college experience were biology courses, right? There's a difference between AP biology, which I took in high school, than there is to advanced human physiology, which I took in college.
I guess this is introduction.
This is chemistry 101 in college, okay? This isn't this isn't chemistry 580, where you're a postgraduate, you're going back for your master's, and you're doing chemistry that is specifically about how carbon interacts with other metalloids, and it's like.
I mean, if the welder needs to know,
Well,
well, the AP chemistry class should spend a couple hours.
Right, but
We should extend this class for 3 years.
yeah, this is less specific. So substitutional. Gotta make this wider. Alloys. So substitutional alloys are between atoms of comparable radii. Okay. Alloys of metals with I don't like the way that this works in Jamboard. This is my one complaint about Jamboard. In order to make the letters smaller, you have to shrink the box, and then in order to make there's more room for the letters, you have to expand the box in a different way. It's a little bit annoying. With comparable atomic radii. Okay. So what happens here is that instead of an interstitial alloy where you get the atoms taking up space between the other atoms, what a substitutional alloy does is, if we have black here, 1, 2, 3, 4, 1, 2. So in a substitutional alloy, you end up with, they just replace each other in the lattice. Okay? So the specific wording that they use is substitutional alloys form between atoms of comparable radius, where one atom substitutes for the other in the lattice. This is the most common brass alloys, which they use zinc as a substitute for copper. Okay, so brass oftentimes looks like a kind of a gold color because you use copper as the base metal, but then you mix in some zinc. And you can see on our periodic table, on the periodic table, the old ptable.com. So if we look at copper here, copper has a radius of 145 picometers. Zinc has a radius of 142 picometers. They're very similar in size, and thus they easily replace each other in the lattice structure.
What about silver and copper?
Silver and copper. So if you were to do silver with copper, so here's copper, here's silver. So these are going to have quite different atomic radii because copper is 145, silver is 165. So it's not terrible, but it's not really that close, right?
Would that be an interstitial alloy or
So an alloy between silver and copper, my guess is that it would be kind of an in-between. And I don't think it would be a very strong alloy for that reason. The atoms, you want the atoms to work well together. And in alloys, atomic radius is one of the most important things that you can consider when you're mixing alloys. And so going back to what Oliver is talking about here, okay? Oliver is talking about these things applied to real life, right? Ancient metallurgists did not know the atomic radius of copper and zinc, but they did know that it worked well when you mixed these two different kinds of things together. They didn't know what was actually happening on the atomic level. And this is the difference between the real world applicability and having the base knowledge of how it works. If we have this base knowledge in chemistry, then we can take it to metallurgy, but we don't necessarily need the chemistry to understand the principles of metallurgy. Does that make sense? Like blacksmiths for millennia have not known about how alloys work on the atomic level, but they do know that certain alloys are stronger than others. Those alloys happen to be the ones that are either interstitial, where the atoms fit in nicely, or they are substitutional, where they replace each other. Elijah?
If based on the locations, like copper is a periodic table, the right next to each other, does that mean that gold and mercury would also work well?
Gold and mercury don't work well together because they are different phases of matter at the same temperature.
They do combine.
You can make with mercury. So the trends, okay, yeah, the trends are, if they are right next to each other, most likely it's going to be a substitutional alloy. If you have something, if you're doing something like yttrium and zinc, that's going to be an interstitial alloy. Yeah.
I think it's molybdenum, but ancient Chinese swordsmiths would dunk their swords with molybdenum.
Oh yeah.
Just, like sprinkle a little bit in and made them like do the break. Like
Yeah.
they wouldn't have to sharpen them as much because they would.
Right, and so
In World War II, it became like a really rare resource because Germany started buying them up for like
molybdenum.
Yeah.
Yeah. So making alloys is one of the most important topics of study for what's the word that I'm looking? Material scientists. Okay, material scientists spend a lot of time understanding how alloys work. And it is, I mean, to give Oliver some credit here, it is one of the most interesting things about material science is alloys and how you can just take a little bit of a different type of metal and put it in with primarily another metal, and you get a really strong, really flexible, really light, or really electrically conductive metal, right? But do we have time to get into the specifics of them? We don't. We simply don't. Okay. Okay, so questions about substitutional alloys, interstitial alloys, or metallic structure? No? Okay. Okay, so yes, Mr. Elijah.
Does bonding ever happen in
Well, where do you draw the line between bonding and just free electron sharing? You know what I'm saying? Like an ionic, electron sharing is kind of like an ionic compound. It's also kind of like a covalent compound, right? What's going on with the electrons? Metals and how they interact is kind of a different thing. It is just like, it is much less rigid in the rules. Does that make sense? Because the electrons can just do whatever in the heck they want to do. They can go there, they can go here, they can go wherever they want. In ionic compounds, you know exactly what is going to happen to the electron. The electrons are going to be by the more electronegative atom, right? In covalent bonds, it's the same way. You understand what is going to happen there. Yeah, so this is why metals behave differently than, for instance, like salt, right? Salt, you can get crystals of salt. Metals don't really do crystal. It's like it's a different situation, right? Because when you make an alloy, you're getting kind of a crystal, but it's not like a crystal in salt. Salt crystals are like, you know, the shape of the salt crystal, right? In metals, you'll have an alloy, but the atoms are just kind of free to be where they.
No, they arrange in specific ways, although the weights are randomly positioned.
Right.
Which is why annealing metals makes them softer, because once those crystals start forming, if they all form at the same time, then every atom is its own crystal, which is what happens if you cool red hot metal in water.
Right.
But if you let them cool slowly,
Then they will align.
And then you'll have less crystals that can slide more easily.
But exactly, but you don't get that in salt. You don't get that in salt because salt is always in that same lattice structure. No matter what happens, they're always going to align that way. In metals, it is kind of like they can do crystals, but they can also do just kind of free form solids, right?
I mean, those free form things are just really small crystals.
Oh, I know, but they're aligned and oriented in way different ways, right?
Yeah.
So it's kind of like taking a snapshot of a fluid, of a liquid, than it is of actually having a solid that is bonded together in one large crystal. Yes.
So, provided that the further left and the further down the periodic table you go, the more metal-ish a metal is. Does that mean that francium is the most metal-ish?
Francium is the most metal. I don't know what you mean by metal-ish.
Like, it has the most metal properties.
Well, the metallic properties comes from the size, because the bigger it is, the less it holds onto its electrons.
Yeah, exactly. So the more left and down it becomes more willing to let its valence electrons run. And this is what, and hydrogen is not.
Does that mean that francium doesn't hold together very well?
No, francium just lets its electrons go wherever the heck they want.
So it would just fall apart.
Well,
francium's super, yeah, and it's super radioactive too. It doesn't occur in nature.
Oh, okay.
Hydrogen, so for instance, hydrogen can start to behave like a metal in the cores of massive planets because they get so hot and so dense that the electrons start to move around.
I saw that in the rest of the movie that you were showing us last time, the melody tube.
Yeah.
The last half of it was the most epic.
Yes, it was quite epic. Okay, questions about that? It is 12:40. This class gets out at 12:50.
Was that all 3 topics?
Nope, we only covered 2 topics.
Let's cover the third one fast.
Okay, we're going to do an introduction to Lewis dot structure. Okay, which is something that you should have covered in your general chemistry class. Who remembers Lewis dot structure? You should all, well, you didn't take general chemistry, Elijah, because you cheated. So, for instance, if I put down oxygen, how would I do the Lewis dot structure of oxygen, Oliver?
You have 1 dot on the top, 1 dot on the side, and 2 dots on the other side, and opposite bottom, or opposite top.
Okay, so this is the way that Oliver thinks that we should do the Lewis dot structure. Lewis dot structure is a representation of the valence shell of a given atom, right? This is very helpful for understanding the structure of molecules, but also what they're likely to bond to. So Oliver said this. Unfortunately, this is wrong. You're really close, like really close. So O. So there are 4 quadrants. Okay, above, to the right, to beneath, and to the left. The Lewis dot structure looks like this for oxygen. You were really close.
What's the difference?
Yeah, there's
You fill it in.
just turn it.
What is the difference?
You know what? You know what I see?
Oliver just turns his head.
Yeah, I see exactly what I see. I think this is all just, yeah.
Okay,
Almost about perspective, Prashant.
what about carbon?
But you have a sideways perspective.
What about carbon?
You got one on each.
Yeah, I was thinking one on each side.
One on each side.
Bonds before that.
Okay, that's the Lewis dot structure of carbon. The Lewis dot structure of nitrogen, so that's oxygen, that's carbon. Nitrogen, so you put the atomic symbol in the middle. Nitrogen is like this. Okay.
Why is the one atom
Yeah.
specifically on the right side?
Okay, so you fill them in.
Don't you mean, like, shouldn't there be 3 empty spots for nitrogen?
Oh,
Because it's in between
I
oxygen
understand
and
what's
carbon.
happening.
Oh wait,
Yeah.
yeah. Sorry. Nitrogen. Sorry, I was thinking. Yeah, I was thinking fluorine. This is nitrogen. You fill them in, starting at the top and going counterclockwise. I know that's obnoxious. So for instance, calcium. Calcium is like C. Okay, calcium is like this.
So, in other words, it fills in the same way that orbital do.
Well, this fills in this is only the valence electrons. So we're not worried about any other shells.
Okay.
So you have 8 valence electrons in each of your noble gases, right? Right. So this lets you see where, like, how many valence electrons it's missing and where they are, so that you can write, for example, your carbon atoms, you know, 1 dot on each side of the carbon.
Yeah.
So if you bond that with 4 other carbons, then your first carbon is completely perfect. It's got its noble gas configuration.
So if we
Other carbons still want their bonds too.
okay, so this is how you do Lewis dot structure for molecules. Carbons. And so if we do this, and now the central carbon is very happy because it gets to pretend that it's a noble gas. Okay?
And all of the carbons around it have 5 electrons, right?
Yes.
Because they're sharing.
And so and these carbons will want to make some other bonds with hydrogen or maybe some other carbons or things like that. Okay? So that's Lewis dot structure. We will cover that in greater detail next time.
So like, well, uranium, for example, has valence electrons of 4s2, 4p2, right?
4s2, 4p2.
Yeah. Like how would
Uranium or geranium?
Yeah.
Well, that one was just like carbon.
Yeah, that's what I meant.
Yeah, so the Lewis dot structure of geranium is the same as Lewis dot structure for carbon.
Okay, so now what if it was 4s2, 4p4?
P4, that's like oxygen stuff,
What would the Lewis dot structure?
it's like oxygen. Everything else is the P4.
Well, would it have two dots, like both carbon?
Okay, pull out your books. Get a sticky note.
I need my questions answered.
Well, the valence shells for all of them in the same problem. So if you're looking for arsenic, that's the valence structure for that one is exactly what it is.
All right, what do we read?
Okay, you're reading pages 410, starting at bond energy. That should be a review from last time.
Whoa, hang on. 410.
410 through 414. Okay, 410 through 414. Next time I'm going to assign you a self-assessment quiz on the material that we've been covering for the past little bit. Okay?
Is there anything else to read?
Nope, just 410 through 414.
Okay, so 5 minutes.
Yeah, it's pretty short. Okay? I'm gonna stop share. And I'm going to say goodbye to Jeanette. Bye, Jeanette.
Bye.
And we will end it there.